Hello, this is Dr. Hisham Said from Santa Clara University. In this lesson, we'll learn about the elastic deformation of axially loaded member. So we learned before about the stress-strain relationship and Young's modulus that relates stress and strain in axially loaded members. Now we'll try to use this information and make it useful for design purposes. So we have here, this is an axially loaded member, very simple case, and with under the stress that's generated by P, you will have deformation delta. Now we learned from previous class or lecture that deformation of a member depends on the material, the load, and the geometry of the member in terms of the length and cross-section of it. Also, we learned a couple of other things. First, from definition of a stress, P is equal to, sigma is equal to P over A. Also, from definition of strain, it's equal to the deformation delta over the original length of the member, L, or we can actually derive the relation for delta to be epsilon the strain times L. We learned about the Young's modulus relation between sigma and epsilon, stress-strain relation. And I can also derive here that the strain is equal to sigma over E. So for design purposes, we need to know under a load case what will be the expected deformation of a member in a system. So I will use what I have or what I know about so far. So delta is equal to epsilon L. I replace epsilon with its relation with the stress, so sigma over E. I know also sigma is equal to P over A. Plug this in the formula, so I will end up now with this cool relation between delta and the load applied on the member, the length of the member, the cross-sectional area of the member, and the type of material used, which is reflected by the Young's modulus. Now, there is a big assumption here that the delta here is calculated for the member that's homogeneous along its length with constant values of P, A, and E. So what does this mean? It means that in general case, where you have like a member with variable cross-section along its length, also variable loads along its length. So I will represent these as a function now of x that ranges from the 0 to the length of the member. So I have px, ax, and the reaction here r is just the resultant, the counter resultant of the loads I have of px. So now delta in general terms will be the integration of all these variable conditions that define the deformation. So P is a function of x. I will integrate over a small length called dx, and I will represent A, the cross-section, as a function of x, and can also represent E as a function of x if the material itself is not homogeneous over that member length. So I can like start with different type of steel, and then kind of over its length changing for, and somehow the carbon content, so it changes the type of steel. But actually that's not the correct example, because all steel with different types will have E. So let's say I have a material that changes its properties over the length of a member. But it's very rare case, so this is why I kind of represent E here as a constant over the length of that member. But also kind of generally in practice, we don't have that case here where we have very tiny changes in P and A. We have actually discrete changes in the P, L, A, and E values. So I can have a structure or a member made up of two materials, but kind of they welded at some point. So in this case here, I have a member or a rod that's actually made up of two rods, L1 and L2, and we have different loads along the length. So in this case, I will replace the integration with the summation. So integration in discrete changes of values, it just translates into summation of the values. So this means that for the delta of this member here, I will have actually to add two delta values, one over the length of L1, because it has homogeneous conditions for the P, A, and E, and I can add delta 2 for the segment represented by length L2. So let's see this example here. I have a cantilever made up of aluminum and brass, and it's not carrying any transverse load, it's all axial, 7 kips, kilopounds, and 10 kips at point C and B. And I want to calculate the displacement of C relative to B. So always displacement here is relative to something, right? So I can move my hand from here to here. From my knee, it's moving this way, but from my head is actually moving toward it. So I have to define the movement of this point relative to what? And usually relative to what is the fixed point in your system. So here, delta CA, this is what I'm after. I need to have other data points here, so I have to know the material properties, and I have to know the cross-sectional areas of aluminum and brass. So always when you deal with deformations, you have to know internal forces. So you can translate that into the displacements and the internal stresses. So I have to draw the internal forces in the member. To do that, I have to do the equilibrium, external equilibrium of that member. If you look here, I have 7 kips going to the left and 10 kips going to the right. So the resultant together is 3 kips going to the right. So the support at A here is having a reaction 3 kips going to the left. So it's very simple. I can do sum of forces and X is equal to 0, but this case here is a simple equilibrium and can solve it on the fly. So now I will draw here the internal axial load diagram. I'll start from the left, like we have seen in the previous lesson. I have my sign convention here is that anything going to the left is positive, anything going to the right is negative, as we covered in the previous lecture or video. So now this support is pulling back the rod. So the rod here is under tension until point B, until it hits 10 kips going to the right. So now it flips here from 3 kips to negative 7 kips internal axial force, which means that part BC is under compression. So now to calculate delta CA, so the displacement of C relative to A is the accumulation of displacements or deformations along the length AC, which is composed of displacement along AB and then BC. So it's basically here delta CA is equal to delta CB plus delta BA. And L3 delta has its values for PL over AE. So just plugging in the values here, the first one, PL over AE for CB, 3 kips is the internal axial force, L is the length here, 15 feet. I have to bring everything to inches because the cross-sectional area is inches. And also my Young's modulus is KSI, kilopounds per square inch. So my 3 kips is complying with the units here, and my length unit is in inches. So that's the first displacement. The second displacement, plugging in the values similarly, one thing I have to make you pay attention to is the sign of the force that's used for delta BA. So the internal force here is compression. So it's negative 7 kips. So that results in that part AB feels elongation of around 0.01 inches. But part BC feels contraction. That part by itself feels a contraction of 0.0089 inches. So when you add them together, delta CA, the accumulation of these two, the elongation and contraction, will result in a net of positive 0.0019 inches. Now, just to confirm here your understanding of deformation, which direction does this deformation here or displacement is happening? Is it to the right or is it to the left? we'll leave you for a moment here kind of to try to visualize. So if you think about it, I'm calculating displacement of C relative to A. So A is fixed. Now point B feels elongation because of the delta AB positive. And now over the length of BC, there is a contraction of 0.0089. So at the end here, C feels the elongation of B, but then feels also that part BC is contracting, it's compressed already, but it's not compressed enough to counter the displacement or the elongation of AB. So net point C moves with the largest deformation in the same direction of the largest deformation I have here, which is the positive, which means it's the going to the right. So at the end here, I can kind of summarize and confirm the direction of the displacement of C is going to the right, because AB grows in length, elongates, BC kind of contracts, but not enough. So at the end, the net is you elongate to the right because A is fixed. So you grow your length and deform positively to the right. So that's the end of this part of the lesson, just introducing here the deformation due to axially loaded members. Next lessons we'll learn about statically indeterminate members under axial loads, and we'll see how deformation and the knowledge about deformation will be our savior in this case. Thank you.